All right, ladies and gentlemen, stress reduction attempt continued. We've got Fall 19 Test 3, Part 4, Question 7. On your test, this will end up being Question 6, as promised on the layouts that we did earlier. And as promised right here, this question will be the same reaction as multiple choice questions 10 and 11 on your test. Now, in Fall 19, this was Question 7 in Part 4, and it was the same reaction as questions 13 through 16. Okay, 4 questions. So we're going to circle the major product, but that's the hard point. Remember, why do we get rid of these 4 products immediately? They're gone. Whoa, we got rid of more than 4 products there. Think that'll happen again? That was bizarre. Let's try that again. Wow. We're going to pause this video. Let's do that first. Stop share. I think we got over our technical difficulty, which was rather amusing, actually. We got rid of these 4 products, and you can finally tell me why. HBr forms with a negative 368 kilojoules per mole enthalpy, and this one's negative 431, which means it's faster. All the HCl's are faster. That's the first question you ask every time. So this is for part A. And the second question is, which CH bond do you have to break to make each of these products? This will make the first product. It's primary allylic. We're going to have to look it up, but I want to look up more than one thing while I'm over there. Okay? That will give that product. This one also from the primary allylic with resonance. But the fact is, it broke the same CH bond. That's all you need to know about right now. Do you realize there's a CH2 here and here, where you used to have a CH3? That's how you know both of those products had that H removed. It's got a different formula on this carbon than it does here with a number of H's and here with a number of H's. This one still has CH3, so it wasn't that H. This didn't change, wasn't that H, but there's only one H here. There was 2 H's here. We're going to have to look up secondary allylic. Okay? And that would give this result. And this one is just secondary, and it gives the final product, which is not a good product. Any allylic is easier to make than non-allylic. So the first 3 are much superior. You don't have to believe me. I'm going to find numbers to prove it. Primary allylic, secondary allylic, and secondary not allylic. How do you know this is not allylic? This carbon right here. It's not adjacent to an alkene. It's just secondary. So we're going to have to stop my share, find the exam, which was actually, I didn't have to stop my share. No, I did. I have to go here, and I have to go back and get that test. I believe it's this one. Yeah. BDEs. I get this. Secondary is 402. I'm just scribbling as I go. Plus 402. Remind yourself why I said plus. Primary allylic, plus 360, right there. Plus 360. Plus 357, we have a winner. Of those 3 numbers, the fastest one to break will be the lowest number. Stop share. Share screen. Sorry. Your numbers are, don't use the bad pen, plus 402. Plus 40, no. That was plus 402. This was plus 360. Primary allylic. The winner was here, plus 357. And that product was the one, oh wow. My arrows. Yeah, there's no problem here. It's just that this should have started from the word secondary allylic. Got it? That is my major product. That is the only major product right there. Highlighter work okay for you? As a circle? 3, 5. We don't have to answer question 3, which is which CBR bond happened fastest, because we're not choosing two products that came from the same intermediate. And then which one makes a CBR bond faster? Not happening here. So there's my A. And B, mechanism for initiation and 2 propagation steps. Init, you got to break the weak BRCL bond. So B. Yeah, we're supposed to write this is called initiation. We'll do it after. You get 0 points for this. I know it seems harsh, but it's a mechanism. You got to show me how that bond broke. Here it is. Half of it there, half of it there. There's all your points for that. The 1 point for this mechanism. And that was initiation. Initiation. And prop 1, use that radical that is going to react. And how do you know which of those two is going to react? You've already made a decision based on one of those radicals picking up a proton. It's not a proton. Badly said. Picking up a hydrogen radical. It's not a proton. It's a hydrogen radical. Which halogen forms a bond to hydrogen faster? Please use Cl dot. Br dot is irrelevant in this mechanism. It is not reactive enough. It doesn't do anything. Okay? So Cl dot picks up a hydrogen from the secondary allylic position. And we got this molecule here, and this is the secondary allylic position. And they are going to hook up, leaving behind a very stable secondary allylic radical. You made HCl. Congratulations. And a carbon radical. Also, congratulations are in order. Negative 431 if you're doing energies. Positive 357. You want to do a delta HP1 in purple. 357 minus 431. I got the 1 minus the 7 is a 4. The 3 minus the 5 is, that's a 2 now. 2 minus a 5 is a 7, and that's a negative. Units, please. Yeah, kJs per mole. It's right on the chart. So if you forget, it's okay. It's on the chart. It says units, kilojoules per mole. Very exothermic. I'm tending to believe this will be the fast step, but I don't know yet. For this to be the slow step, the next one has to be more negative than negative 74, right? That's very rare. That's a very negative reaction. Step 2, prop 2, not step 2. Prop 2. Take the radical you just made. It's always the same pattern. And I think I gained a carbon there. Don't do that. The radical's kind of high up there. There we go. Plus a non-radical called BRCL. Yes, 99.9% of your BRCL has not been used. Yeah, it hooks up. You get CL dot. You know, you're tempted to put a meow there, but it's not really a catalyst. You didn't start with it, did you? You didn't add CL dot in there with a little spatula. No, you can't call it a catalyst. It's an intermediate. But you used it in step 1 and made it in step 2. It's got that in common with a catalyst. And you get what up here? Br. I think we have to look up that bond. Secondary allylic CBr and BRCL. Secondary allylic CBr and BRCL. I don't think you're going to see what I do this next time, but I'm looking those two things up. Secondary allylic CBr, and I'll write it down. You won't see it. You're seeing it in the classroom. It's 228 with a negative sign in front. Can't write with that pen. Why a negative sign in front of negative or 228? Yeah, why? Because I formed it. It was this one. And BRCL was broken. CLBR, BRCL, plus 219. Coming back. You should be where I am right now. I think in the video, we never left the screen. That's okay. We found our numbers. Stick with the purple theme here. Delta HP2. BRCL was positive 219 to break. Making CBR secondary allylic negative 228. 8 minus 9 is 9, and it's a negative in front. Kilojoules. That is definitely not as negative as the previous one. Rate. Don't waste your time writing rate determining step. Don't waste your time. Do this on the test instead. You just go and point to it here and say RDS from now on, Dr. Whitaker. Point to it. So you've defined it. And now you can use RDS as many times as you want. But you got to explain how you can use delta H to predict that prop 2 is the rate determining step. You got to use good words. You can't always say delta H can predict which one's faster. You can't. Under what circumstance can we use delta H to predict which step is faster? Only delta G can be used to predict which one is more spontaneous. Delta G has delta H in it. What else does delta G have in it? Delta S, which is entropy. You need to make a small statement here that acknowledges that you know that entropy does not change in these propagation steps. So you say when delta S equals 0. You got to say that, or else you're throwing away a point. And then the next point's real easy. When that's true, delta G is roughly equal to delta H. You got another point right there. You haven't even made a sentence, and you got 2 points. So the least exothermic is slower. And negative 9 is less exothermic than negative 74, right? Prop 2. We good? Prop 2. And D, transition state time. Oh, that was D. What was C? Calculate, we did. Yeah, this was all D. We did the C's over here, and we didn't do reaction, did we? That's okay. We can easily edit a C to be a D. right? Maybe, I don't know. Not so easy. And C was here, here, and here. Delta H RXN equals negative 74 minus 9 equals negative 83 kilojoules per mole. Need units on a final answer. That's the end of C. Was C, right? Yeah, good. Then E is about transition states, and so is F, right? Does the rate determining step involve an early or a late? So before I do my answer, I'm doing reactants and products is exothermic. Try to look up there, reactants, products. This is much closer to the transition state, which is up there, right? Transition state's above both these hands. This hand's closer, and that's reactant. Early. Put it in words first. Here's your words. And see if I can get it even shorter than I did before. It's not a short explanation. In an exothermic reaction, the energy, you got to talk to me about energy. And TS wasn't defined earlier, but you're going to do it right now, right? What's TS short for? Transition state, point to it. And say, I'm calling it TS from now on. Hey, I even left out the period. That'll make it even easier. Bye-bye. Bye-bye. The energy of the TS is closer to the energy of what? The reactants of or the product? Tell me which one. Yes. But you're not done. You just stated a fact. But it has nothing to do with what the transition state looks like. You have to say, making a subtle argument here, Dr. Whitaker. So if its energy is similar, its appearance should also be similar. So write that down. So it should look more like reactant than product. And we need F. We need the symbol for a transition state. Square, square, telephone. Telephone pole outside. And the element that's transitioning in Prop 2, give me the one element that's moving from one molecule towards the other. Br. In the beginning, Br is real close to Cl. It's bonded to it. So I'm going to put Cl over here, starting to lose its bond to Br, but just beginning. And Br is ending up on carbon, right? Ethyl allele right there. That's it. Notice early on, Br and Cl are bonded. So in an early transition state, they're still pretty darn close to each other. In the end, C ends up with Br, but that's late. Okay, almost there. G. GHI. Give the mechanism to termination, explain why they're supposed to be avoided, and explain how to avoid them. Pick two radicals that you drew already. I like the opposite of initiation for termination. That's just an easy one. It's a guarantee. Whatever you wrote for initiation, flip it backwards, call it termination, easy point. Give me hooks though. There's more than two termination steps. I just want two, and I want you to make your job easy. I mean, in English, the opposite of initiation is termination. Forget about science, right? The word, they are opposites. And then you got to tell me why it's bad, just based on which reaction you shut down. Which of the two prop steps did you just kill? You made Burkle. You made Burkle, and in H, whichever of these steps required one of these radicals for the reaction is now shut down. So the first one, you just killed prop one, just right, killed prop one. That's why it's bad. And you can do another one. How about, this is one of my favorites. There's a termination step between the alkenes. If an alkene meets an alkene, you get a termination step. And it's a product you definitely don't want. The dimer. There. And that's I. Which one did you kill this time? The one that required the carbon radical from prop 1 and prop 2. The carbon radical is required here, and you just killed it here. So you killed prop 2. And the only way to avoid this is to keep radicals from seeing each other. Make sure they see other things. So the sentence that's good for everybody on Wednesday is right here. H. Oh, there was a nice modification in the morning section. I can't remember how she said it, though. It was last week. I put her in the video for initial. She said it better than me. I say keep radical concentration low. That way a radical is highly unlikely to meet another radical by shortening the, language gets my students sometimes, because English is not their first language. So when I say shortening the length of time that you put the heat on, does that make sense? What's a better way for you guys to say it? I don't want this kept on for a very long time, because that's what creates radicals. So what wording would you like to say? Keep the amount of time that heat turned on to a very minimum. Exposure, you like that? The exposure, lessening the amount of time that the reaction is exposed to delta. Does that work? I like that. Lessening, you guys know that. Shortening, I don't know. You think tall and short when you see that, don't you? You don't think of time and short. I understand that. It doesn't make sense. By, what do we say? Lessening the exposure? Lessening the time of exposure. Lessening. I still think Miss Brinker had a better one. The time of exposure to delta. You can write heat if you want. And I'll just remind you, yeah, heat was up there in the form of delta, right? Either one, you put the delta or the heat, you don't have to put both. And that's it. And I'm calling it. It's been a long day.